Here we go, the final torsion test of the series, and this is being performed by our own Ed Chen. Ed is he's the only experimentalist of the TA group this year. Rahul and Dave both do primarily computational modeling, where Ed actually does experiments on materials, so he's the right guy for this class. So here again, he's going to perform the difficult stunt of getting the specimen loaded in there with the flats aligned correctly, and with the other hand, he's able to one-handed do this. So that's typical of an experimentalist, right? He's just done this a lot. He's done a lot of material testing. He makes sure it's sitting firmly in there. And now the acrylic will, just like it did in compression and tension, will behave a little differently. So he's going to put that safety shield around it. Of course, he's got to get the fixed chuck and the load cell, torque cell aligned, and so he's kind of at the mercy of the previous user, so he's going to have to jog this one way or the other to make sure those flats line up. Looks like he's got to open the jaws just a little bit more. Turned it up to the high-speed jog, get it adjusted. So Ed is in fact an experimentalist, but he also saw Rahul and Dave just go through this, so he's got the luxury of experience from watching the other two guys. Narrating a torsion experiment is a little bit like narrating golf or a dog show or something like that. Sometimes you just have to watch. But I think there's value into seeing this whole thing because it takes time. These experiments take time, and there's a lot of nuances and subtleties to getting them to work right. There are many, many, many places to make a mistake, misalignments and unexpected loads. So as you think about your projects for the semester, which I hope you're thinking about already as you wake up and go through your daily routine, what materials do you rely on throughout the course of the day, and how are they loaded? This one will be in torsion. Get both jaws, both chucks. All three jaws in each of the two chucks have to get tightened down. The safety shield is in place, so he's going to go over. Unfortunately, the mouse is behind the inset right now, so he's zeroing the channels. And then I suspect he's going to go down and click on play. Can we see that? Oh, there he clicked on play already. Okay, so very quickly we can see that torque increase, albeit in the counterclockwise and hence negative direction for this particular machine. And the test begins. Keep in mind that we're treating acrylic as a brittle material. It's actually somewhat viscoelastic, but for our purposes it's brittle. You can see it's already the torque is no longer increasing linearly with the angle of twist. And do we have one full twist on here already? It seems as though the rate of rotation is a little higher now than it was for the others. It turns out because acrylic has this viscoelastic property to it, it's visco, meaning it flows, albeit very slowly, but it's also still elastic like many other metals and construction materials. We can see we achieved kind of a maximum torque. I can't quite read the numbers in my voiceover screen, but we've reached a maximum torque, and then the torque started to decrease right away. And so now we're starting to level out a little bit at some steady state torque. What are we at? 400 degrees, so we're approaching one full rotation, or we're slightly over one full rotation, so we should be able to see that black line. And the reflection on that safety shield is such that we can't see it terribly well. But I bet Rahul, the trusty cameraman, sure enough, yeah, there he goes. He's going to give us a different view. Maybe we can see the black line. Yeah, now we can see it. So we're at over one full rotation, approaching 2 full rotations now. The torque is leveling out at some steady state value on this brittle material. Actually viscoelastic, but we're going to treat it as brittle. And we'll see what happens to brittle materials when we try to twist them too far fairly shortly. 246 approaching 800 degrees, so we're well over 2 full rotations at this point. Still pretty good for a brittle material. But of course the numbers of rotation, the angle of twist is kind of a function of how long it is, right? So the longer the specimen, the more twists we'd be able to get for the same material. There again we can see on the right side, I think that's a coincidence that on the right side the lines are starting to bunch up, so there must be some little micro cracks starting to form on that right side. Ooh, bang! You can see one big piece and several small pieces kind of exploded out of that failure region. The torque dropped down to 0. And so let's slide the tailstock out of there. The safety shield goes away. There's that chunk. Some little chunks, one big chunk. There's a very distinct smell when acrylic fails. It's kind of a hot plastic sort of a smell. And what's really interesting about this is what the aluminum, the ductile material, failed at on a perpendicular surface, perpendicular to the angle of twist and perpendicular to the axis of the specimen, whereas this brittle material, acrylic, failed at kind of a 45, I mean it's a twisty, turny kind of a 45 degrees, but there's definitely this 45 degree component. Where's that chunk? Back up to the chunk. There we go. So there's Dave holding the fracture surface for us. So definitely something that has to do with 45 degrees there. And again, you'll learn about why that happened a little later in the semester in your Mechanics of Materials course. Ed is going to save his data. Of course, it saves it in this proprietary format again. So he's going to give it some file name. Looks like Ed is going to keep the file extension. He's carefully giving it a descriptive name. Now he's going to ditch the file extension. Experimentalists tend to collect hundreds and thousands of data files, so you get good at coming up with little systems for naming these files. Now he's got to open that same file. Now it's saved in the proprietary format. He's got to scroll down and find it, of course. I guess it's time we clean this up. He right clicks on that to export it. Export this. Where do you want the resource to go and what do you want it to be? We'll use comma separated variables, a .csv file. Save it somewhere smart. Again, a little walk down memory lane for me. All the former TAs and all their folders on here. It's kind of fun. I have fond memories of working with a lot of these people. Ed makes his own folder, saves the CSV in there. And that's what we need to do. Now he'll be process that data. Thanks, Ed.